In this video, I will introduce you to some of the frameworks that are commonly used for machine learning, in particular deep learning. First, I'll give a quick overview of some of these frameworks. Then I will show an example of one of them in action. There are many frameworks that are used for deep learning. This slide lists a few that have been popular over the past couple of years. Some of the most common ones that we see or hear about today are Tensorflow with Keras and PyTorch. Keras acts as an easy-to-use front end to a couple of other frameworks, most commonly Tensorflow, but also Theano and CNTK. Caffe2 merged with PyTorch in 2018, as they were both developed and maintained at Facebook. Most of the frameworks are written in Python or have Python front ends, but Julia also has a growing number of machine learning frameworks, including Flux and KNet. Tensorflow is probably the most well-known deep learning framework. It is open source, which means you do not need a license to use it, and was developed and is maintained by Google. Tensorflow is a Python-based framework. It can run both on a CPU, the usual processor that a computer uses, and a GPU, or graphics processing unit, which is a specialized type of hardware that is particularly fast at doing the mathematical operations used in machine learning. You'll learn more about GPUs in the next unit. TensorFlow implements neural networks as a computational graph, where nodes represent mathematical operations and edges represent n-dimensional arrays, or tensors, that carry data between nodes. TensorFlow tends to be fairly low level and can be tricky to use, so many people use Keras. Keras is a high-level framework written in Python, but also has an interface to R. It is most commonly used as a front end to TensorFlow. It's great for fast and easy prototyping, and it supports a wide variety of layers in neural networks, including convolutional and recurrent. A typical workflow in Keras is pretty straightforward. You instantiate a model class, sequentially add layers, and then train the model. This is great and pretty easy to use if you're working with standard layers, loss functions, and optimizers, but isn't the most flexible if you wanted to do something out of the ordinary. PyTorch is another open source framework written in Python provided by Facebook. It's based on Torch, which is another framework that uses the Lua scripting language and includes components from Caffe2. PyTorch provides its own data type for n-dimensional arrays, the tensor. This is like a NumPy array that can live on a GPU. The PyTorch workflow is a little more involved than Keras, but allows for more flexibility. You would first define a class for your network where you initialize the layers in your network in the constructor, and define a function forward that defines how data moves through the network, or the functions used to traverse from one layer to the next. From there, you would specify a loss function and an optimizer, and then write the training loop. Rather than specifying a number of epochs and calling a single fit function like in Keras, you write your own loop to iterate through the epochs. At each iteration, you would feed your training data through the model and then calculate the loss and the gradient using the backward function. The backward function is generated by PyTorch from the forward function that you define. Finally, you would take a step down the gradient determined by the optimizer you've chosen. PyTorch is definitely more hands-on than Keras, but does provide functions to use within the training loop so you don't have to write your own loss functions or optimizers. However, this workflow does allow the user to more easily replace any of these steps with their own code, say if they wanted to try a novel loss function or optimization method, or add in any extra logging or stopping criteria during training. For this reason, PyTorch is often used in research. Next, I'm going to show you how to develop, train, and use a model with Keras. Before I do that, I'll explain the problem a bit so you know what's going on. We're going to be training a convolutional neural network for the MNIST dataset. The MNIST dataset contains 60,000 black and white images of handwritten digits, 0 through 9. Each image is 28 by 28 pixels, which can be expressed in a matrix or array of intensity values from 0 to 1, 0 being black, 1 being white. As its name implies, a CNN contains convolutional layers. Each convolution is followed by a pooling layer, and the entire network usually ends in one or more fully connected layers. There may also be dropout layers. The final output layer uses a softmax activation function to give an output like a probability for each class. Before we go into the example, I'll briefly review the types of layers you'll see in CNNs. A fully connected or dense layer comes from the traditional neural network, where each neuron takes a weighted sum of all inputs, adds a constant or bias, then applies an activation function. In the image above, layers 1 and 2 are fully connected layers. A convolutional layer contains a number of kernels or filters and performs a convolution for each on the input. A convolution is a mathematical operation on two functions. The 2D convolution we are talking about here slides the kernel across the input matrix and at each step does element-wise multiplication and then sums the result. The kernel is a small matrix of values that are determined during training. Pooling layers are used to reduce the size of the input. For example, a 2x2 max pool with a stride of 1, as shown here, takes the maximum in each 2x2 box in the input. Pooling layers do not have any trainable parameters. Finally, dropout layers are used to prevent overfitting. They will remove or drop out units in the network. Briefly, our CNN for the MNIST dataset looks roughly like this. We take the 28x28 input image and put it through a convolutional layer with 32 5x5 kernels, or filters, followed by a max pooling layer to reduce the size by half. Then we have another convolutional layer followed by a max pooling layer before we go through two fully connected layers to produce our output, a length 10 vector. The index of the largest number in the output is the predicted class. Now let's take a look at how we can implement this in Keras. The first thing we'll do is import the functions we need. From Tensorflow, we'll import Keras's model and sequential classes, the input, dense, flatten, conv2D, and max pooling 2D layers, categorical cross entropy to use for our loss function, and the atom optimizer. We have our own utils script where we have a function for reading our data, and we'll use matplotlib for plotting. Next, we'll build our model. The Keras framework has two APIs you can use to build models, sequential and functional. The sequential API is good for simple networks with a linear sequence of layers. If you want to do something a little more complicated, say where layers have multiple inputs, the functional API will give you the power to do that. In this example, we have a fairly straightforward CNN, so we'll use the sequential API. We'll define our input shape, the size of our images, which is 28x28, and the number of classes, the 10 digits 0 through 9. We'll instantiate the model with the sequential constructor. Then we'll add a convolutional layer with 32 5x5 kernels and the ReLU, rectified linear unit, activation function, followed by a max pooling layer, which will reduce the size of the output by half. This is followed by another convolutional layer with 64 5x5 kernels and another max pooling layer to further reduce the size by half again, resulting in 64 4x4 matrices. The result of that is flattened into a long vector before it goes through two dense, fully connected layers. The final layer has a softmax activation function to make the final output a number between 0 and 1, like a probability. We can print out a summary of our model to check it. The summary will tell us the output shape of each layer and the number of trainable parameters, or weights. Next, we'll load our data using the readData function we got from the utils.py script. This script loads our dataset and splits it up into training and testing data. Here we print out the number of samples and shapes of each. Next, we'll compile the model. This is where we specify the loss function, optimizer, and the metrics you want to use to determine the success of the model. As I mentioned earlier, we're using the atom optimizer and categorical cross-entropy for a loss function. We also specify accuracy for our metric, which is usually what you want for classification problems. Next, we'll train our model. We'll need to pick a batch size, the number of samples we calculate the loss function for at a time, and the number of epochs, or the number of times we cycle through each batch. We then run fit to start training. At each epoch, Keras will let us know how our model is doing by telling us the loss and accuracy on both our training and validation sets. I'm going to fast forward this portion of this video so you don't have to wait for it to complete. As you can see, our model took roughly a minute to train. To evaluate our network, we can use the output of the fit function to get the accuracy of our model at each iteration. We can make a nice plot of accuracy versus epochs to get an idea of how training progressed. If we want to actually use our model later, we'll have to save it. Then, when we're ready to use our pre-trained model, we can load it and make a prediction. Here we are classifying our first test sample. We get a vector of 10 numbers. The index with the highest value will be our predicted class. In this case, our model is predicting a 7. Now let's look at a few of our images to confirm. We'll use the imShow function to plot each image and put the predicted value in the title. As you can see, our network does a pretty good job of classifying digits. As a teaser for the next unit, I've restarted my notebook on different hardware that includes an accelerator called a GPU. I'm going to retrain the model again. Recall the first time it took about a minute to train the network. Now that I've added a GPU, it's training in about a quarter of the time. In the next unit, we'll talk more about the role hardware has to play in machine learning and why GPUs work so well.